Yes, so this is a continuation of Eric's talk, essentially. And yes, so I will take it from where he left it. And so the plan for the talk is first to see, we'll see essentially how Mathlib does it roughly, how Mathlib constructs all this hierarchy of algebraic structures, and then how morphisms are constructed in this hierarchy, and subobjects and quotients are constructed at the end. So most of the talk will be on the first part of this plan, though. And so what is the beginning? You could, one of the most basic structures you can define is semigroup. Semigroup. So well, you already seen what a group was. So this is a little bit less structured. And is it visible? Hopefully, we're back. Okay. So so here, for instance, would be how you would declare an additive semigroup that is a type alpha, and you see here the extends keyword that you already learned, and extends add. Add alpha is just saying that there is a sum. So it makes sense for when you have two terms of type alpha, it makes sense to add them. Okay, with no properties, it's just adding them. You have and that's the fact that there is an addition and also a notation for it, the plus. And so a semigroup is this together with a proof, or a proof of the fact that of associativity, which you can see it here. And okay, I used additive, an additive. I declared an additive semigroup. I could have done a semigroup, and so here is exactly the same. Now it's extending mol alpha. Mol alpha is just saying that you have multiplication, which is written with an asterisk, and mol assoc, which says, the multiplication is associative. And you can see this attribute here to additive. What that tells Lin is to link these two classes together. So unfortunately, ideally you would want to skip defining the first thing, the add semigroup, but Lin still asks you to do that in the future. I'm told that the idea is to remove this, and so you will just do doing the second declaration will automatically do the first. So that would be a semigroup. If you want it to be commutative, then you can create a new class, which now it's done also in the two. It's a semigroup which is also commutative. So you can concentrate on the second declaration here, and that's similar to what you've done with group, but now there's very few axioms because this doesn't have much structure yet. In particular, for instance, there is no 1 or zeros in there. Okay, so it's just an addition which is associative or possibly also commutative. Yes. So once you have that, then you can consider monoids. So what is a monoid? Well, first of all, you can introduce a new class. Again, this is so that everything is as reusable as possible. There is a new class that puts together the fact that there is a multiplication and then there is a 1, and the 1 should be a neutral element for multiplication. So mol1 class, it extends 1 alpha and mol alpha, and it has these two axioms, 1 mol and mol1, which say that 1 is the left and right inverse, left and right neutral element. And of course you could have the additive version of it with the attribute, but we'll do it in the next slide. Yes.
So what would be the function of 1 alpha?
What would be the
function of the class 1 alpha? What would it feel?
Oh, 1 alpha. It's just specifying one element. Yeah, I didn't put it in here, but if you look at the Mathlib, this is defined. It's a structure that has, well, a class that has only one member that says it's called 1, and it's a term of type alpha. So it specifies an element of alpha. That's going to be the 1. And from now on, you'll be able to use the notation number 1 to refer to this element. Yeah. So that's, and the 0 similar for 0. Yeah. Once you have that, then a monoid is just putting together these two things. So it's a class which extends these two classes, semigroup and mol1, with no extra axioms or data. So there is nothing below. Okay, so that's how you actually do it. You don't have to put the where. There is nothing. Okay, so that's a monoid. So monoid is you have a multiplication and a 1, and 1 is a left and right neutral element, and it's associative. That's what a monoid is. Okay, and there is some magic already here that Lin does for you, because there's two moles, there is two notions of multiplication that you would have, and you could worry whether they will be the same or not, right? Because being a semigroup had a semigroup extends mole, so you have a multiplication coming from semigroup. But at the same time, mole1 class has also extends mole, so you have a multiplication from there, and so you could worry about whether this will create trouble, but it doesn't, because Lin is smart enough to notice this, and actually it will only consider one mole. There will be on one mole. So essentially, what you'll have, well, you can check when you type check monoid.mk. Lin tells you this thing below, and you can see that to create a monoid, you on a type alpha, you need that alpha is a semigroup. That's the first argument after extends. But the second argument, it's not in here. You don't see mole1 class in the second argument. What it did, it broke it into the constituents, and so it asks for a 2-1, which is an instance of 1 alpha, and the axioms. Okay, so there is the mole is inside the semigroup, right? So it already does for you. Now you have these two semigroups. So if you have a monoid is a semigroup. So you can, if you have a monoid alpha, you can do alpha dot to semigroup, and that will be the fact that this alpha is a semigroup. And you could think, well, but also a monoid should be a mole1 class, so you should have a function that's dot to mole1 class, and it seems that it's not here, but it actually is there. So when you did this class monoid extend semigroup mole1 class, apart from taking the mole1 class apart and asking just a 2-1 and the axioms, it also created this dot to mole1 class function, so that from the user point of view, it's like symmetric. You still have, from a monoid, you can still get the two classes it extends to, but one kind of is privileged because you have to put it in when you create it, and the other one, it's added artificially. Yes? Yes. Oh, does someone know about universes? When you put type, it's a synonym, I think, for type 0, and for most mathematics, I care about. I'm fine to stay in there, but sometimes you need to be a type on some universe, and this would be a universe. I don't know more about that. So I think from here, if you put type, so far it would still work. But some of these definitions, I took them directly from Mathlib, so they are maybe.
So I guess one of the ways to see it is that type contains things. Type 1 contains things that contain things, and so on. So the more nested you need, the higher the type universe has to be. And so he allows for definitions to be universe polymorphic, which means that they get this U as a parameter, so that you're not dependent on a specific depth of type nesting.
So I don't know if you will learn about this anymore in the week, but to me, I usually ignore this. It seems to work, but yeah. So yeah, as I said, I mean, there is an additive version. Again, you still need to declare it, class add monoid, and it would extend add semigroup and add 0 class. I just put it in this slide, and so you can, if you forget to add the attribute, you can add it later. So I added the attribute to additive to the monoid class in the previous slide. And one thing you have to do, remember this to mole1 class that I mentioned that Lin adds for you as a new function, because to restore the symmetry between the two classes that you are extending from. That one doesn't have the additive version automatically added. So you have to add manually this attribute. So I don't know if that's something so that Lin, it would be desirable that Lin does it in the future, but so far you have to create this to additive version manually by adding this attribute yourself. This existing says that that this tumal1 class it already exists. So you just want to link the two, but you don't want to create again because it was already made. So otherwise, if you delete this existing link, will complain to you. So what is this? What is the advantage of these two additive labels if you have to still duplicate everything? Is that the lemmas don't get duplicated. Lemmas get automatically generated by Lean under the scene. So here is a lemma I can state and prove about monoids. So it says if you have a monoid M and you have three terms A, B, C, and well, if B times A is 1 and A times C is 1, then B equals C. Yeah, so the inverse is, yeah, if you have a left inverse and a right inverse for A, then the two must coincide. Yes, so this is a lemma you can prove using one mol, mol-a-soc, mol-1, and so on. Okay, so these are multiplicative. It's a multiplicative proof of a multiplicative lemma, and automatically Lean adds a new lemma, which is called, well, it translates the name. So left is left, but inf becomes neg, and for instance, 1 would become 0, and so on. So it has some automatic translation of the name. So I can check this theorem exists already. It was created, and you can see what it says. You see, it takes an add monoid instead of a monoid, right? And the hypothesis also gets translated. You know, instead of B times A equals 1, you now have B plus A equals 0, and A plus C equals 0, and the conclusion is the same. So this already got stated and proven automatically for me. So again, yes.
How does it know that it becomes neg?
Well, because that's how two additive works. It's like a dictionary. How you translate, 1 gets translated to 0, the number 1 gets translated to the number 0, the word 1 gets translated to the word 0, the word mol. This is Lean. Mathlib is doing it, right? I guess. Yes.
It's not written here, but it's somewhere in the code.
No. It's somewhere in the code, hidden very deep that you never see it. I think. You when you write the Lean file, you'll see in the exercises you'll download this file, and it has this tag here to additive, and that's it, and you don't see anything else. And right below it. Yeah, but this is done all behind the scenes. You don't see anything. The next line after this, you can have actually literally this check here, and it will output this. Yeah.
Will you be able to find it in the documentation?
I believe it's there as well. Yeah. Yes. Okay. Commutative monoids. Well, commutative monoid is well, now we can build it already from what we have because it's a monoid, but it's also an additive commutative semigroup. Okay. So that's it, and then you can have the additive version. Okay. The commutative monoid means just the multiplication is commutative, right? So that's how you, yeah, sorry, a commutative monoid would be just a monoid which is also a commutative semigroup. So again, no extra data, just these two facts, these two classes. Extending these two classes is enough. So now from here, now you could finally get groups. Again, a group, it's a monoid with an inf. An inf is just stating, yeah, you have a map from G to G that you have also notation for it, which is to the -1. And the extra axiom that's this inverse is a left inverse. It's an actual left inverse for every element. You don't need, that's enough to show. I mean, these are the minimal set of axioms for groups. You can prove that is also that this left inverse is a right inverse and so on. Yes. I don't think that's no. You go from you go, yeah. Yeah, it just, the idea is, as in the previous talk, you could do groups with an arbitrary operation, but Lean chose to do it multiplicatively. But then also you want the additive version, and so And so instead of duplicating everything, you have this code that's running that's helping you.
So what would be our use case for this? Will we ever have to, I mean, groups and so on, they exist. Will we ever have to use such a thing?
Say?
When would you yourself use such a...
Well, anytime you want, I mean, this is how groups are. So if you have some type and you have an operation on it, and you want to state the fact that it's a group because you want to use lemmas that apply to groups, you will have to instantiate these classes, right? So if you either you want to prove a theorem that applies to groups, then you will want to say let G be a group, and then things about G, and then in the statement and in the proof you will be able to use multiplication and oh, this two additive. Oh, so
when this has been done, it's good that we just but will you as a user ever use this?
Well, right now I'm already using it because well, so far because it's only one operation. No, but in the next slide I will want to define a ring. So I'll want a multiplicative structure and an additive structure playing nicely together. So I need at least two operations, right? And so my operation Lean allows me to use either multiplication or addition for an operation on a monoid state, but it has different names. So the use of it is.
When will we as users of Lean ever want to use the command add to additive? Like when will you actually need to type it? Because it seems like all the basic things of groups are already there.
Oh no.
And, is there any use for this outside of the theory of groups?
Or no, yeah.
We use this when we want to prove maybe a new theorem of groups.
Anytime you have. Yeah, does anyone what's the last structure that has been added to?
For example, I'm doing stuff about measurability of functions. I write a new lemma saying that because measurability is relatively new, say, so I write a lemma saying that if I have to measure a function, then multiplication is, and I don't want to copy it and write it for addition as well. So I just put that into the. Each time I define a new concept that will both do multiplication and addition, it saves me half the time.
But you have to suppose that the proof also still works.
Yeah, exactly.
Yes. Yeah. So in the example I gave you of that lemma, all this will get translated, right? One mole will get translated to 0 add. Mole ASOC will be add ASOC, and mole 1 will be add 0. Yeah, so. Okay, so again, commutative group is just a group which is also a commutative monoid, right? Commutative monoid, it was only adding the axiom that multiplication was commutative, which is all you needed. Okay, so that seems quite straightforward, and then you get to rings. So now you need two structures, and so what's a ring? Well, a ring takes a type R, and well, you want. Well, R should be an additive group. It should be a monoid. So additive group already is for the addition, monoid for the multiplication, and also it has to have a mol 0 class, and you need. So it has a 0 for so the mol 0 class states some axiom about 0 with respect. So what 0 is 0 times x should be 0, and x times 0 should be 0 as well. And also you need distributivity, so you have to add these as axioms. So that's fine. That's a ring, and what's and for instance here you can prove this is how you would prove that a ring gives rise to a commutative group. So if you forget the multiplication, and that's a fun exercise. I left it in the exercises to prove this. So if you have a not necessarily commutative ring, and then you forget about multiplication, so the addition is automatically commutative. Okay, you didn't need to put this in the axioms.
So if I, in the previous slide, if I were to just instantiate additive group, would I then not be able to use the theorems about groups? Or do I need to put the additive stuff?
Yeah, additive groups are not groups. They're separate from Lin's point of view, right? So an additive group it has a 0, and a group doesn't have a 0, for instance. So they're kind of separate. It's so that you can use. So what you want to do is, that's why you want to prove the lemmas about the multiplicative version, and then use these two additive tag to translate to the additive version. Everything is duplicated, but it's duplicated, but you don't have to type it. That's the idea. Okay, so yes.
So in this in the example below, where
No, in here.
When it says like bring to active group, is this automatically constructed? So when we have some inheritance.
Yes. This to add group it's given to you by Lin automatically. So when you use this extends command, you have these two to whatever functions. The thing is that, as I said, some of them are kind of members of the class, but some of them get added artificially later on because Lin broke the other arguments to avoid these repetitions. Okay.
So okay, maybe it's the same question. So if you write, so you have instance additive at common group R.
Here, yeah.
Is this, adding this, does this amount to the same as if right away in the definition of the ring, I would have written extends at common group?
Yeah, this is not how Lin is doing it. Mathlib is not doing it. So in Mathlib, the commutativity for addition is already put in the axioms. This is just an illustration that is actually not needed.
The question is, does it end? Is it the same?
Same as in equally the same. As definition, I need to ask the experts. I don't know. Let me.
There is a little difference, but as a user, you don't really have to learn, because you generally construct a ring by using these curly braces anyway. Then it doesn't really matter how it's nested.
So
I see. So the level of nesting, the organization would be different in here, but if you use the skeleton, it will generate the proper one, the correct one.
I guess my question is, if I forgot to define ring and I forgot to write the position commutative, and then I add this instance thing, then afterwards I can just pretend that I
yeah.
rings are commutative.
No, you can assume, you can in your lemmas assume that you have a ring, and then that like your expert hypothesis holds, but you cannot prove that.
Yeah, but I think what he's saying is, yeah, if you have a ring later on, after proving this, later on, anytime you have a ring, any statement about that any lemma that uses the commutativity will hold for that, right? Yeah. Okay, so once you have this, for instance, now you can prove that Z is a ring. Okay, so if you do, that's how you do it. You say ring Z, and then, well, you can autocomplete. Well, you can do this underscore, and then ask Lin to generate this, and it generates all these fields, and you can keep. Now this is actually full proof, but it's cheating because it's using the properties that we already know for Z. So it just, yeah, associativity, we already, there is a proof in Mathlib for associativity in Z, so we just put it in here. If we had to prove it from the definition, it would be much longer. Yeah. Root is so add ASOC is already in the namespace. So if you want to refer to the one outside of the namespace, you put root. So it's kind of the base. It's outside of this my particular namespace. It's using the global one somehow. Yeah, and here it's using the ones for integers, mul add and add mul. Probably here, if I put int.mul ASOC, it should also work. Haven't tried. You can try on the VS Code. Okay, so that's that so far. But then, okay, the next thing we want to consider is modules over a ring. So if you don't know what the module is, it's a vector space, but the field can be a ring instead. But think vector spaces if you want. Now we need an extra operation now, which is on different types, right? It's the scalar multiplication, and so we'll have a new class called small for scalar multiplication, and it takes two types, alpha and beta, and it's mapped from alpha to beta to beta. So it takes an element of alpha and an element of beta and outputs an element of beta. And it has notation. This is this you enter with backslash smul. At least that's how I do it. And so that puts the notation. This is already existing in MATLAB. I just copied here so that you saw what smul is like. So if you were asking before what mul class is, it's very similar to this one, but with a multiplication, and the type is the same. It's only one type. And then now you could define what a module is. So now module there is a parameter which is a ring R, right? And then M, which is, and now M is a parameter, it's not extending at so sometimes before you could wonder why ATCOM group is in here instead of being after it extends. Okay, so why is this syntax? Well, and then the axioms below, right? So why do I do it like that and not, or MATLAB does it like that and not that? Well, the problem if you put if module only depended on a ring R and an M and then extended all these properties, it will this algorithm that looks for the right class, it would keep looking for R's without, I mean, M and R wouldn't be linked a priori, and so it would be looking for some unspecified type R with which was a ring, and that would take forever. So this is fine because here as small RM, both R and M get mentioned. So the rule that you can follow if you create classes is that what you're extending of, so this what appears on the right should always depend should depend on all the parameters that are in your new class that you define. So M doesn't depend on, so ATCOM group is ATCOM group for M. It doesn't depend on R, so you don't want to put it in the extends. Okay, so that's what a module is. And
I have a question before. So that the 73 in the annotation, this is like the level of annotation?
Yeah, this is the level of precedence. I don't know. That's I think what's in MATLAB, and I don't know why it's 73 and not. There's also you can put high, low, and medium or something like that. But this is. Does anyone know how do you make it? That's my experience how you do it, but not. Yeah. I never know how to do this, but.
The only constant is that function application is 1024.
Okay, so it depends on whether you want to take precedence over that or not, and yeah.
So the priority is from the highest prioritized or the lower?
The higher, the more priority. Right?
Multiplication has a higher priority
than addition.
So that's big enough.
Yes. Okay, but 73 is there because there is some 72 or 74 line? Aha. Okay. Okay. So from here, for instance, you can do things like creating, from here you are showing that if you have a ring, then you get a module over the same itself, right? So it's if you have a ring R, then you have a module. So R is a module over R, yeah. And then you have to. So what is the multiplication by scalars? It's just the actual multiplication on the module, on the ring, and then you can prove all the axioms for that. So that's fine. Another thing you can do is if you have an abelian group, then is a Z module as well. Yes. Here, why this worked? Yeah, if you look at the code, this is copying code from what you will see in the exercises, and sometimes I exported certain functions into the namespace so that I could call them. So probably that's why this worked. So I wasn't meaning to take a close look at this, but the zero mode, yeah, I don't know which zero mode this is actually calling right now, but probably it was in my namespace already because I had exported it. You'll see. Yeah. So as I was saying, you can make a Z module. An abelian group is actually the same as a Z module, but here what I'm going to prove is that if you have if you're given an additive commutative group, then you get a Z module automatically. So first, I will define separately what's multiplication by scalars in this case. So and you do it, well, I do it in 2 steps. This is this NS mule. NS mule doesn't need that you have an abelian group. You just need you has a 0 in addition, and then you get a multiplication by the naturals, which is a map. Yeah, it takes a natural number, an element of m, and it outputs another element of m, and you define it by cases. So this 0 and anything will give you 0, and then the n plus 1 term times a is the same as a plus n times a, right? So that's multiplication by natural numbers, and then you need to define the multiplication by integers. Now you need, in addition, that m has a negative, and then, well, the integers are defined as either natural numbers or the negative of a success of something that's not 0, and then in the 2 cases you define what the multiplication would be. So once you have these, then you can, of course, you could put this inside in the instance below, but then it could take longer. So that then you can create this instance. There is an exercise here to fill in the stories, but yeah. So you say that how you get a module out of this additive commutative group. Well, the multiplication by scalars is exactly this function that you just defined above, and then, yeah, multiply by 0 and by 1. It's very simple, but then that multiplication and scalar multiplication play nicely, and distributivity and so on. You have to work a little bit. So I left them as stories. But that's another example. And the reason I'm showing this is because this leads to a problem. Problem is that if you now take Z is a ring, and you can get, this would give you 2. Why is this? Sorry, I just noticed something. If you have a ring, you would get, Z is a ring, and therefore you get 2 module structures for it over itself, because first, Z is an abelian group, and so if you have an abelian group, then you get a Z module. So, but also, since Z is a ring, then it's a module over itself, and so it's also a Z module. Yes, so you have 2 ways of constructing a module over Z for Z, and this is called a diamond in Lean, because you can think of here you have ring, and then you have module, and then and one direction, and then this module in the bottom, and this can be bad, because then if you need the module structure for Z over Z, which one will Lean take? And Lean, you can ask Lean which one it takes, but this might lead to errors, right? So what you would want is to make sure that these 2 constructions match. So anytime you have a diamond, you'd like that the 2 ways are the same. And how you build this into the system? Well, it's first of all, anytime you forget, if you go to a structure that has more data, more fields, than to another one that has less fields, or it's poorer structure, you want to be forgetting data when you go in that direction, not defining extra data, which is what we did here. So because we had this, you remember we had this NS mul or ZS mul. So what you have to do is put that inside the definition already, and that's how Mathlib does it. So what you will do is the add monoid class that we had will make it a little bit more complicated. So the new add monoid class starts as before, but then we add these extra 3 fields. So an additive monoid, it's an additive semigroup which with a 0 with a 0, such that but also with a multiplication by the natural numbers. Now, the thing that's on the right is the default for this. This is what Eric was saying in the previous talk, that sometimes you can delete some fields, and Lean won't complain about them because they have default values. And if you delete them, he tries to use the default values. But here, I'm saying, in principle, an additive monoid, you would have to provide an NS mul field with 2 proofs that they behave well with the 0 and with successors. Okay, yeah, and here, well, you say that if you have an additive monoid, then you also can multiply by the naturals. But once you have this extra data here, then for instance, the integers would be an additive monoid by, now you have to complete this data. You to specify, this allows you to specify which is the multiplication by the naturals that you want. So having these extra fields is useful. And probably if you see, when you see how topology hierarchy is built, that also is an issue that you have to deal with. So you solve it by adding these extra fields all the time.
Sorry, can you go back?
Yes.
So in NS mul.
That's the multiplication by natural numbers.
Yes, and then you wrote, I mean, the right thing is the default, right?
Yeah, that's the default.
It's its own default.
NS mul is this right thing. This NS mul here is actually it means this one, the one I defined here. By default, you will try to apply this lemma, which if m has a 0 and an addition, it will work. So if I don't put anything, it will use that one, and a multiplication by 0 and so on. It's right. You see, even has default proofs. So if these proofs work, then fine. Okay. And yeah, so Z is an additive monoid, and yeah, that would make everything work. So for, again, here to emphasize, here in general you don't specify this, but if you care about the actual additive monoid structure that Z has, you can specify now these extra fields. That's the idea.
Sorry, can I ask once more? So aren't we here in the namespace where NS mul refer to the inner one?
Well, this one refers to the inner one because this is not yet there, I guess. So, and this one refers to this one just defined, I believe.
Okay, but the other one does not. Okay. So
here it doesn't conflict. It's not defined yet. That's I think it's happening. Yeah. If you are in VS Code, hovering over everything, it tells you exactly which version it's using. So it's in here it's more cumbersome. Okay, so with this, then you should be able to read what's in Mathlib and see all these things that you will see in this structure. I will show you a picture of how complicated it is now in Mathlib, all this hierarchy. But this is how all the abstraction you're seeing in there happening. Why all this abstraction is there? Okay, so here's the picture of, well, this might be outdated, but that's all the hierarchy starting from field and below. Eric gave this graphic to me, and if I click, you can see, maybe you can identify some things that use. There is a semi-ring, commutative semi-ring. You see that these are in camel case because that's the Lean 3. This is a Lean 3 diagram taken from Lean 3 Mathlib 3. So now they look very much the same, but with a camel case. And you can see monoid with 0, commutative monoid, commutative semigroup, and so on, semigroup. So that's, and here on the bottom you have has mul, has 1, which now are called mul and 1, for instance. Okay. So you see that yeah, this, I don't know how to get back. How do you go back? Backspace. Huh. Does anyone know how in a browser you go back to this? Control 0? No, no, no. This is no, no.
Okay, I'm sorry.
If I now.
You can press Alt arrow and then the left key. So you bring the previous page
No. Oh yeah, yes, yeah. That worked now. Okay, great. Yeah. All right. So on to morphisms. I have until 1 minute more, or no, 15 minutes. 1 minute. Okay, I'll go a little bit over time. Yeah. Okay, I might skip the third section, but okay. So now, how you do morphisms between these structures? Okay. So the first thing you could think of is, well, just do a predicate. So a prop. So you make a definition which outputs a prop. And so, for instance, given G and IH to monoids and a function. So this f from column G to H is just a function. Then what is monoid Hom naive? Well, is monoid Hom would be, well, that you would ask that f of 1 equals 1, and that for G and G prime, f of G prime is f of G times f of G prime. But that's hard to work with because of this conjunction. You have to keep splitting it and so on. So maybe instead, better yet, is to make it into a structure. So you've seen. So you could create a structure is monoid Hom. Again, that it's the two monoids and f, and then you have two axioms or two terms, map 1 and map mol. You don't want to make it into a class, but you could say it like that. But Mathlib option is what's called bundled morphisms, which means that at least for morphisms of algebraic structures, it means that the information about the function is inside. So is inside. It's part of this structure. So instead of a parameter. So G and H will be monoids, and then the first parameter will be this 2fun, which is getting the function out. It's a function plus extra with axioms about it. This is called bundled. There is other types. Sometimes Mathlib does the other option. For instance, when you have maps between types which are topological spaces, a function being continuous is like a predicate, like the other one. But for algebraic structure, it's more convenient to do it with this bundled morphism. And you can tag it with an X label, as Eric told you. Now, what you want is to be able to apply this monoid Hom to elements, right? You want, if you have a monoid Hom, so you took all the care to actually prove that it maps 1 to 1 and it preserves multiplication. You'd like now to apply to an arbitrary element of X, and you could do, you have F, you could do 2fun F X, right? But you want to avoid using this 2fun, and so what you can make it is that this can be, that such a morphism can be coerced to a function. That's what you do with this coef1 class, and it just takes you just have to specify this coercion. What is the map, and it's this 2fun. So you specify that this 2fun will give you the function from G to H, and with that, it would automatically allow you to apply it to elements. If you add this coe attribute to 2fun function, to the 2fun function, what it allows you is that whenever instead of in the info view, instead of seeing the 2fun, you will see that little arrow for coercion. So it's more convenient. And once you have that, then you can do things like that. If you have monoids G and H, and you have a monoid homomorphism F, then you can evaluate, say, F. You can say F of 1 equals 1, and that makes sense to Lin because he knows that F, even if it's not really a function, can be thought of as a function. But if you look at this in VS Code, you won't see F of 1, you'll see arrow F1, because it's not F, the monoid Hom, which gets evaluated at 1, it's the coerced into a function version of it. Yes?
So how do we refer to the choice of coercion here?
The choice?
Yeah,
no,
when we say it's an instance.
Once you say an instance, as Eric was saying, when you will do this when there is only one way. So given a monoid home from G to H, there is only one way of thinking of it as a function from G to H. And so that's when you prove this instance and you say, yeah, it's this map. And so this is just this specifying the function from G to H that it's part of the data of the monoid home.
And it saves us somehow that we can use this for.
This COE you could use. No, but you're not meant to use this COE explicitly. It's just because you made it into a COE font. It means that this COE font is a class that says that your type can be thought of as a function. Of functions actually you specify from G to H. And so from now on, anytime you do, whenever Lean sees f of x, it says, oh, so f is not a function, but can it be thought as a function? Yes, because it's in this, it's an instance of this class. How does it get considered as a function? Oh, it looks at this COE field and it says, oh, applying the toFun function, and then that's when it evaluates.
When there's a mismatch of the types, and checks if there's a coercion, if an instance of this coercion exists.
Yeah, well, mismatch. I mean, if you are applying to an element, yeah, you expect it to be a function, right?
But I don't need to type this up our list.
No, in this case, no, because he can figure it out. Yes, but VS Code will display the info view will display it. If the info view, the thing on the right of VS Code will display that arrow. You don't need to type it, but he will display it so that you know it's not f itself, because otherwise you would be wondering why it says, what does it say f of 1? F is not supposed to be a function. So, yeah. Okay, so again, you can have additive versions of it. Well, this you have to create the structure, you created yourself, and you create the instance, and you add the attribute. So that's how you would do it. Now, if you want to do ring homomorphisms, you get into a new problem, which is I don't think there is in this case. That's how I saw it done in my lab. So yeah, you have to do it all manually here. It's only for the lemmas that they get translated, unfortunately. The lemmas will still get translated. The lemmas you prove about one thing will get translated, but with this defining these structures and these instances.
If I prove something about the real, like the multiplicative homomorphism, it will automatically prove what the additive.
That's what I believe. Yeah. Okay. So if you want to consider ring homomorphisms, you would do it like that. It would be a monoid homomorphism, which is also an additive monoid homomorphism. So it's a morphism both in the multiplicative and in the additive sense, because R and S have multiplication and addition. The problem is that then how do we do this COE? Where do we? If you go back to this slide, in here, how do I mean here I was tagging this function with a COE attribute, but where would that be? Because there is no toFun for ring homs, because ring homs extends this too, and so first I would have to take it to monoid hom and then toFun. So it will be a composition of two functions, not a function directly, and I can't put it in there. So instead of that, what Matlib does is do more abstraction. Yeah, I'll stop in after this slide. Yeah.
I just have to let Eric into my office because he has another talk to do. But you can continue.
Okay, I'll stop soon. Sorry. Yeah. So how you solve this is adding more abstraction. So what you will do is add a class that says this is at least as good as a monoid morphism, and so this new class is going to be called monoid hom class, and it will have a toFun and a map1 and map-mul. Here you'll add the COE attributes and everything. This looks a lot like what we did before for monoid hom. Now it's monoid hom class. So this specifies that your class is at least as good as a monoid hom. Let me skip the yacht param. It's something I don't fully understand anyway. But then now once you have this extra layer of abstraction, now you can prove these two instances very easily that say that both monoid hom and ring hom are monoid hom classes. So They are instances of this new class that we just created, and it's very easy. For monoid homes, you just the toFun is just monoid home.toFun. For the ring homes, how you prove that the ring home is at least a monoid home? Well, the toFun, it's you compose these two. That's you first apply two monoid home, and then you apply toFun. So here's where you have this composition I was mentioning. You still have to put it, but the coercion and everything will work automatically for it. And what this gives you is that, for instance, if you prove a lemma, this lemma says that if you have two elements, so you have something that's at least a monoid home, and you have two elements such that mm prime is 1, then f of m times f of m prime is also going to be 1, right? So you prove this lemma, and once you have this lemma, now you can use it in both in the setting of monoids and then in the setting of rings. That's the idea. Why? Because both monoids and rings, both monoid homes and ring homes are monoid home classes, and so Lean will infer that automatically and use this lemma in both cases. So you see these two examples are proven using exactly that same lemma. That's what we just plot. There's one more abstraction you can do. Instead of using this toFun directly, you can extend a class called funlike, which encodes the fact that your class can behave as a fun, so it has a coercion to functions. There is a class for that, and also it also records the fact that when the two homomorphisms are the same if the underlying functions are the same, and so that's included in this funlike. If you have a class that's funlike, that behaves like a fun, it means that when you forget all the structure and you just record the function, that map is injective. Okay? And so you could prove it and so on. And yeah, and as I said, I will skip the sub-objects and questions because of lack of time, but I'll put available, I make these slides available soon, well, this afternoon, at least in the form of a PDF, so you can check them. Still, all the content of the slides is already contained in the exercises in a Lean file, so you can look at the comments and you can read essentially everything there. So I think that's, yeah, I will skip the rest. Which was not too much, but it's already very late.